Hello everyone, my name is Hao Mo, a PhD student from Pengcheng Laboratory. Today I will present my paper, SCDM, Scope-Based Channel Denoising Model for Digital Semantic Communications. This work is a collaboration with Dr. Yaping Shun, Dr. Shu Mingyao, Professor Hao Chen, Professor Zhi Yongchen, Professor Xiaodong Xu, Professor Nan Ma, Professor Mei Xiatao, and Professor Shu Guangchui. My presentation will include 6 parts as shown on the slide. In part 4, I will give you a detailed description of our proposed scope-based channel denoising model. Let's begin with some background information. According to the International Data Cooperation's recent reports on global annual data generation, by 2025, the world's data generation is approaching 200 gigabytes, which is equivalent to 20,000 billion gigabytes. How to transmit massive data in the coming decades remain a global challenge. Semantic communication is an emerging technology in recent years. Powered by AI, the core idea is that when transmitting data, we only transmit its semantic extracted from the original data. This allows us to send a minimal amount of data. At the receiver side, an AI-powered decoder can reconstruct the original data. The received semantic data then can be used for downstream tasks such as segmentation or object detection. The transmission payload is much more lower than the traditional compressed methods, for example, JPEG or BPG, and the AI-powered transmitter and receiver guarantee the transmission fidelity. There are 2 main types of semantic communication system: analog semantic communication and digital semantic communication. The key difference between them lies in the transmission channel used, either analog or digital. The digital semantic communication is more compatible with modern communication systems. Now we introduce our motivation. In current digital semantic communication works, the received noisy data is fed directly into the decoder. This requires considering channel noise during the training stage of encoder and decoder. A common approach to solve this problem is adding noise according to the channel SNR levels during training. However, this process can often lead to training instability. Another limitation of current digital semantic communication system is the need to train different codecs for each specific SNR level. This results in substantial training costs and increased storage requirements, which can hinder deployments on both the transmitter and receiver sides. Recently, a paper titled SCDM Channel Denoising Diffusion Models for Wireless Communication introduced the use of diffusion model technology for denoising in analog communication channels. The author aligned the diffusion forward and back-forward process with the analog channel's noise correction and denoising process. Most importantly, their model can handle denoising for different SNR levels within a single model. However, SCDM can't use in digital modulation communication system. As the slide shows, the forward process of SCDM misaligns with digital communication channel noise corruption process. During the data corruption process, the mean value gradually transfers to 0. At the final step, the noise data centering around 0 of the constellation, while for digital AWGN channel noise, the noisy data only centering around the constellation points. Now we introduce our system model. Our digital semantic communication system is composed of a conventional AWGN digital communication system and our proposed score-based channel denoising model. It's worth noting that the score-based generative model is a variant of the diffusion model family. Now we provide a detailed description of our proposed score-based channel denoising model. We briefly introduce score-based generative modeling. It's composed of a forward stochastic differential equation process and a backwards SDE process. The score here means the grading of log probability of the data distribution. During the training stage, we train a neural network to predict the score. At the sampling stage, the direction of a learned score will pushing the sampling value to high probability of a data distribution, allow us to sample high quality data from Gaussian noise. Now we connecting score-based generative modeling to digital transmission. The corruption process of digital channel can be viewed as a forward process of a SDE process, and the denoising process of received noise data can be viewed as a backward process of a SDE process. We first analyze the digital AWGN channel corruption process in discrete form. Here, Z0 represents the transmitted data, and each sigma I corresponds to a particular channel SNR level. With the expression of Zi-1 and Zi with Z0, we can further derive the relationship between Zi and Zi-1. We utilize the fact the sum of normal distribution random variable remains a Gaussian, with mean being the sum of the two means and the variance between the sum of the two variances. With the result of previous slide, we now transfer the discrete representation into continuous representation. Then, according to Kolmogorov backward equation, we can derive the continued backward SD as follows. Finally, we discrete this process during sampling process. Notice that the GT score function was replaced by the score predict from neural network. The algorithm as three parts: the training of SCDM, sampling, and the joint training of SCDM and an encoder-decoder. For detail, please refer to our paper. Now we present our experiment results. The experiment set are as follows. We use Cipher 10 as our training and testing data. The codec is VAE, and the number of channels we use is 128. We use 64-com modulator and SNR range set from -18 dB to 18 dB. When using ZCM as our baseline, we observe a 5 dB improvement in terms of PSNR at SNR equal to -12 dB. In SSRM measurement, we demonstrate a 0.08 performance enhancement at SNR equal to -6 dB. We also compare the semantic codec MSE performance with JCM. Notice that after denoising by SCDM, the semantic code errors are reduced, especially in the low SNR region. We also visualize this process on the right side. In summary, we proposed a score-based denoising diffusion model for digital semantic communication system. We align the forward diffusion process with the noise corruption process of digital communication channel. We elevate the storage bottleneck with a score-based denoising diffusion model that can handle different channel SNR levels. Our model can serve as a plug-and-play module for future digital semantic communication system. Thank you for listening. My email is written on this slide. If you have any problems or questions, please feel free to contact me.